Hello, this is Dr. Viv. Let's solve the following variation on the classic yo-yo. Now, if you have a yo-yo, normally you would send it down by holding the string and letting it go straight down. That's not what I'm doing here. I'm letting the yo-yo travel on a rough incline of angle theta. So here I have a simulation of what I'm about to do. If I let this yo-yo now rest on this incline, imagine that this end is fixed to a support, and that support is fixed to the incline. Well, generally speaking, the yo-yo will not move, but if the angle is steep enough, then it would start to move. It would start to rotate clockwise actually and work itself down. Alright, so that's what I'm looking at in this example. Then I look at different limits. What if the incline is really smooth? And what if the angle were 90 degrees? So let's solve this variation on the classic yo-yo problem. The first part is static equilibrium. We have to ask under what conditions the yo-yo remains absolutely motionless. So for that, let me redraw the incline here. The critical angle is theta naught. At that angle it begins to slide, or rather, it begins to slide and roll at the same time. We'll examine that in part 2. Let's draw a big nice figure so we can see everything. Now, generally speaking, in a yo-yo the central shaft is not that big, but to make our analysis very clear, I'm making that pretty big. The tension acts like that. Now when it's about to slip, it's going to go clockwise, which means that the force of friction must act in the opposite direction as the direction of the impending slippage. That is the force of static friction maximum at the moment slipping is occurring. There are two other forces. I'll draw the normal force lightly so as not to obliterate details of the yo-yo. And then you have the mass times gravity, mg, or the weight of the yo-yo. Without that weight, nothing will happen. So my coordinate system is going to be adapted to this motion. So x is going to be downward and y is vertically perpendicular to the incline itself. Now initially there's no motion, so I don't have to draw any of my acceleration vectors here. This distance is little r and this distance is capital R. Let us start by writing Newton's laws of motion. The sum of forces in the y direction is 0. This is going to be true for the second part also. Well, that tells me the normal force is equal to the component of gravity perpendicular to the incline, and that is mg cosine theta naught. Now generally the force of static friction bears no relationship to the normal force, other than the force of static friction is less than or equal to mu times the normal force. But if it's maximized, that less than sign can be replaced by the equal sign. So I have mu s times the normal force. So that is mu s times mg cosine theta naught. Now in the x direction, there is initially no motion, so sum of all the forces in the x direction is also 0. Well, that tells us the forces on that side, which are tension plus static, must equal the force downwards. So I get Ft plus FFS max. The component of gravity down the incline is just mg sine theta naught. Now what I'll end up doing is actually use the expression for friction that I have here. So I get Ft plus mu sub s mg cosine theta naught is equal to mg sine theta naught. Let me call that equation 1. That by itself will not enable us to solve the problem because you don't know what the tension is and you don't know what mu sub s is. We need another equation that relates somehow tension to something else, and that is got by the rotational condition that the sum of all the torques about the center of mass is 0. The torques can be taken about any point, but I choose to take it about the center of mass in this case. So that means the clockwise torques must equal the counterclockwise torques. The clockwise torque is Ft times r times sine 90, and the counterclockwise torque is F sub Fs max times r times sine 90. Sine 90 is 1, so I won't write that. So I get Ft times little r equals F sub Fs max times capital R. Well, that gives me the value of tension. And since I know what the friction max is, I'll write it down. Times mu s. I'm going to call this equation 2. All I have to do is put 1 and 2 together. So 1 and 2 put together gives me, if you notice, there's a r over r mg cosine theta times mu sub s here, and just mu sub s mg cosine theta here. So I get r over r plus 1 times mu sub s mg cosine theta naught when I add them, and that is equal to mg sine theta naught. Observe that mg cancels out, so mass and planet don't matter. That gives me mu sub s. I'm going to write this as r plus r divided by r, so when I invert it I get r over r plus r times tan theta naught. Now this should be compared with what we had for sliding objects. When objects are about to slide, the angle of friction tan theta is equal to mu. In this case it's more complicated. You have these radius factors. Now this is always true for any rolling object. For example, if I had a cylinder instead of a yo-yo, the only difference is that little r would be equal to capital R and this factor would be half. So it's still different than a sliding object. Now let's assume that the yo-yo is moving. The figure is almost identical to this figure, but I'll draw it anyway because it's a separate problem. The angle need not necessarily be different, because as you know, when objects just start to slide, they can continue to slide at a smaller angle. So we'll just not bother changing anything about the figure there. We'll just write theta instead. Now I'm going to redraw the yo-yo. The big difference this time is there's motion. As a matter of fact, it's going to rotate clockwise because it's being held back by the thread. It's a thread that's slowly giving out and causing this thing to rotate clockwise. In the process of rotating clockwise, it also accelerates downward with with acceleration a. Now, what is the relationship between a and alpha? You would be wondering, how can we use the no-slip condition? Because slipping is how it gets down. There's plenty of slip here. But there's no slip here. The thread is not slipping. So we have to use the small radius r to implement the no-slip condition. And that's about the only significant complication here, or rather the observation is that you have to use little r instead of capital R for the no-slip condition. The rest is just like any other rotational problem. Because there's plenty of slip, of course the force of friction will kick in. This time it's kinetic friction. And the other forces are just there as usual. There's a normal force, there's a gravity force. Incidentally, I'm doing the gravity force much smaller than it actually needs to be, because if it needs to go down, the gravity needs to be really big, so that the component of gravity along the incline must exceed the sum of those two forces as drawn. So this figure is certainly not to scale. Let's proceed and solve this problem. So first of all, we have to implement the no-slip condition at the thread level. That condition is A equals little r times alpha. Everything else remains, so in the vertical direction nothing changes, so I'll just write force of kinetic friction is mu k times Fn, that's known as the law of friction, and the normal force is just mg cosine theta, so that's mu k times mg cosine theta. In the x direction, now the equation is going to be sum of all the forces in the x direction of the center of mass is mass times the acceleration of the center of mass. For rotational problems, I always like to emphasize that the center of mass is involved. So the component downwards for gravity is mg sine theta. That's helping acceleration, so it comes with a positive sign. Tension is not helping the acceleration, and the force of kinetic friction is also not helping, so they come with a negative sign. And all that must equal ma. Let's call this equation 3. Then we have the sum of all the torques about the center of mass equals the moment of inertia about the center of mass times alpha about the center of mass. Now I just told you the moment of inertia of this yo-yo is I. You can actually calculate it. If you know the density of wood and standard moment of inertia formulas, you can actually calculate the moment of inertia of that compound pulley situation. But I'm not interested in doing that here. We'll just take the moment of inertia to be I. Now again, here I'm going to take the philosophy that all the torques that help alpha are positive and all the torques that are fighting alpha are negative. So Ft is helping alpha because r cross f is in the same, r cross f is into the page and alpha is also into the page, so that is helping alpha. This is not, because r cross f in this case is out of the page and alpha wants to be into the page. So for those reasons, we're going to write Ft times r times sine 90 minus ffk times capital R times sine 90 is equal to I alpha. Let me implement the no-slip condition, which is up here, and write alpha equals A upon little r. I want to find tension from this, so let me do that, because tension is an unknown. So Ft equals capital R over little r ffk plus Ia over r squared. Let's call this equation 4. What I'm going to now do is substitute equation 4 into equation 3. So I'm going to get mg sine theta minus, there is a term ft there and there's ft here, which involves ffk. So when I put the ffk term, it combines with that ffk term, so I'm going to get minus r over r plus 1 ffk, which is mu k mg cosine theta. And then because I have a negative ft, this term also comes there, which is negative ia over little r squared is equal to ma. And this equation can be solved for the acceleration. I guess I can do that like this. I'll take all the acceleration terms to one side, so I get m plus I over little r squared times a equals everything else. So that's going to be mg times sine theta minus r upon r plus 1 mu k cosine theta. And let me do two things. Let me divide both sides by m. If I do that, this will become 1, but I have to put an m downstairs, and then finally I can divide by that factor. So I'm going to get my acceleration, which is what we want. It's g over 1 plus I over mr squared times sine theta minus r over r plus 1 mu k cosine theta. I just want you to observe that if the acceleration is 0, we are back to the static case, so this term will become 0, but that will give us exactly that, with mu k being replaced by mu s, because nothing's happening. So we do get the limit. The third part of the question is the other limit. What if the floor or the incline suddenly became smooth? What then? What if mu k is 0? If mu k were 0, this term disappears. And so the smooth limit, smooth incline limit, gives me mu k equals 0. So the acceleration is simply g over 1 plus I over mr squared times sine theta. Well, g sine theta is just reduced gravity. So you can imagine what happens when theta equals 90 degrees. When theta equals 90 degrees, you just have that. So that's just regular yo-yo play. Whenever you play with the yo-yo, you just let the string down and it goes straight down. So that's just regular yo-yo play. Theta equals 90 degrees. In a previous video, I analyzed that, and you should check that the expression I got is the same. So for regular yo-yo play, a yo-yo is just g over 1 plus I upon mr squared. So that's the limit.